Hello everyone, welcome back to Daily LeetCode Live, where I do the daily question raw and uncut. So we finally have a hard today after like 2 or 3 weeks, and looks like it is some graph problems. So let's see. So minimum cost walk in weighted graph. So let's see the bounds and let's see what we have. So we have n, which is an int. And then we have, so I think that's the number of nodes. We have edges, which is going to be like a list of edges with the weight, I think. Yeah, looks like it. And then we have some query, which is again a list of ints. So what does query look like? So query is two numbers, maybe like getting from somewhere to another place, maybe. Yeah, but let's see. So we have 100k nodes, 100k edges. Yeah, so that the length of that is 3. That's normal. Yeah, okay. So let's see what it wants. So there's an undirected graph. Yeah, so that's kind of what we guessed. And then the edge as well. A walk on a graph is a sequence of vertices and edges. Wait, actually, how many queries are there? Also 100k. Okay. So a walk on a graph is a sequence of vertices and edges. And the walk starts and ends with a vertex, and each edge connects the vertex. Wait, the walk starts and ends with a vertex. So it's a circle. So it goes back to the original place, I think. And each edge, yeah, connects the vertex that comes before it and the vertex that comes after it. It's important to note that a walk may visit the same edge or vertex more than once. Okay. So the cost of the walk, starting at node U, ending at node V, is defined. The cost of the walk is defined as the bitwise end of the weights. In other words, if the sequence of edge weights encountered is this, then the total cost is going to be and. One thing to notice for and, so we want the minimum cost, right? One thing to notice for and is that whenever we do, like, let's say W1 and W2, is always going to be smaller than W1 itself. Because like if it is, so like for W1, if the binary representation, if it has a 0, well, it'll keep being a 0. But if it has a 1, there's a possibility that W2 is going to make it 0. So it's only going to get smaller. So maybe we want to walk as much as possible, and it says that we can visit the same edge or vertex more than once. So right now, like, I'm thinking maybe some connector components, something like that. So you're also given a 2D array query, where query I is equal to SITI. So for each query, we need to you need to find the minimum cost, and if it is no such walk, the answer is -1. So let's see. So return the array answer, where answer I denotes the minimum cost for query I. So yeah, we definitely need a n or log n. We need a O1 or log n way for each query. And yeah, let's just see like exactly what a walk is, because like it's a bit wordy up here. So if we want to go from 0 to 3, we can walk. Yeah, so we can go from 0 to 1, 1 to 2, 2 to 1, and then 1 to 3. So what would the weight be then for that case? So 7 would be 4 to 1. Right, so if we don't use this edge, like 7 and 7 is just going to give you 7 back, right? But if we also add 1, well, these are the only set bits, so it becomes 1. Yeah, so like it goes back to my point. When you do AND, it's better to always like just add more stuff if you want to minimize the output. So if we look at this, so if we want to achieve like from 1 to 2, if we want to achieve the minimum, so achieve the cost of 0 in the first query, we need to move on the following edges. So and we are allowed to go to the destination and walk away. Okay, that's good to know. So that means we just have to find connected components. And so that there are two situations, right? The first one is like for each query, the first situation is if if your two nodes are in the same connected component, then you can technically just like walk through every every edge, and you can like do the AND thing, right? uh and like you just get like 15 and 7 and 6 and 1, which would give you 0. The other uh the other situation is something like 0, like 3 to 4, like where they are from different components. Then we just we can't work there, so we just return -1. Yeah, so I think we need a way to store all the connected components, and then we need a way to get all the edges of that component, and we want to we want to store like the AND thing for it. So so what we can do is we have groups. So this is going to be like for node I, which group, so which connected component does it belong to. So we will set it as -1 for in range n, because we have n amount of nodes. So again, we can just do a DFS. Actually, would DFS work? I think it should. Yeah, DFS would definitely work. So we have some DFS here, and then so just want to do for I in range n. If groups I is equal to -1, then we do want to do a DFS on I. So this is going to be the node. So we'll just call it node maybe. So that's going to be the node, right? Oops. And otherwise, that means it has been seen. It is already in a group, and we don't have to deal with it. We also probably need a group counter. So group count, maybe like up here. So group count, we'll start at 0, of course, and then so after you run the DFS, we have to increase the group count. So the next group is going to have a different identifier. So, and then I guess like we can do the we can do the AND operation like during the DFS. So I'll show you how, like what I have in mind. Yeah, so the other really important thing we have to do, we have to turn edges into adjacent list. If not, it will be too slow. So adjacent list. So we need the node and the weight. So let's mark that. So we'll store node and then weight. So it will be a list for all the nodes. And now for ABW in edges, adjacent list A, we want to append B and W, and then here we want to do otherwise, because it is undirected. So now we have an adjacent list. We are good to go for coding the DFS. Yeah, so so what we want to do is when we get to a node first, we want to mark that node. So groups node, we want to mark it as group count, so the unique identifier. And then we want to loop through, we want to get all its neighbors, right? So for next in adjacent, should do next time wait in adjacent list of node. So if next is already seen, so if groups next, oh no, if it is not equal to -1, well then we want to do something here, right? Wait, actually we should have the and sum. Yeah, sure, we'll call it and sum. So the and sum is going to be this thing here. Because like we are basically doing and for everything. Terrible variable name, but we just do that for now. Yeah, so we need a because like we actually haven't seen any edges yet here. Wait, actually can query be the same? Like can the two query number be the same? So length is that. Doesn't say anything, right? So what if? Yeah. So what if si and ti is equal? Oh, okay. It says it can't be equal. Okay, so we don't have to. Yeah. So yeah, we need a way to like just keep doing the ends, but we need a placeholder first as well. So we need something. Wait, what is the largest? The largest. Wait. Okay, so it's like that, right? So that means we need yeah, like we need a bit mask as the original thing that is all ones. So like when that thing end like any number from this range, we should still get the same number. So I think like we can just do 2 to the power of 20. So that's going to be oh, I got a better way. So we can do this and then we shift it, I don't know, like maybe 15 and then we -1. So that's going to be like 14 ones, right? And wait, is that big enough though? It should be. Wait, what is 2 to the power of 14? 2 to the power of 14 is... Oh, it's way too small. Yeah, we need something bigger then. We just do 2 to the power 20. So 2 to the power 20 is a million, right? But it doesn't really matter here. We just do that like as the initial mask. So if groups next, well, if it is not equal to 1, that means we haven't seen that yet. So the end sum, we need to end equal to DFS next. And then of course like we'll mark it here and then we do the same thing. Wait, yeah, true. What if there is like no edges? Wait, if there are no edges and you do the end, it's just gonna end this. Yeah, so it wouldn't matter. It wouldn't matter. Yeah, so if that we just want to do this and then at the end we can just return end sum. So when we have gone through everything, so let's say we start at 1, like it's gonna do like 15, 6, 1, and then like let's say it does 15 first, it is going to. Oh, but there could be multiple edges. Is that true? Oh, there could be multiple edges though. Well, that would be a problem. Yeah, maybe DFS isn't the best way of doing it because like we might not see some edges because there could be multiple edges. So what if we get the connected component first? So like in this case, we will get 0, 1, and 2. And then for each edge, we can basically just check like which group like one of them is in, and then well we can just we can just like add the wait okay, so if an edge has 0 like on one side, and we know that 0 is in some group, we know that the other node is going to be in the same group, right? Is that true? Yeah, that should be true. Yeah, so we can, yeah, let's not worry about the end sum yet. Let's just yeah, let's just get all the groups correct for now. So just do none here. So you just want to get all the connected components. Yeah, so maybe that means we don't actually even need this. Maybe. Yeah, I don't think we even need this then. Like the adjacent list thing. We'll comment it out for now. Maybe we need it like in the future. But basically what I have in mind is we can just loop through all the edges. So at the end, so let's say we have 2 groups. At the end, group count is going to be 2, right? So we can just make the end sums. And we can do, well, again, we have a placeholder. So -1 for something in range group count. And then for each of the edges, so we want to get the group of node A. So that's gonna give us the group, right? And then we want to update the end sum. So end sum of group A. We want to do the AND operator with W here. Yeah. So we have that now. We should have all the. So we should have all the ends like for each connected component now. And then what we can do for the queries, so for AB in, is it called queries? It should be, right? Oh, it's called query, but there are multiple queries. Okay, yep. So for AB in query, so if group A is not equal to groups B, well, if they're not in the same group, they're not connected. So, let's see. So yeah, we can have an answer list. So answer.append. Well, -1 because we can't actually get there. Otherwise, we want to append groups A and like the end sums of group A, and then we can return answer. Let's see if it works. Adjacent list is not defined. Oh yeah, of course we actually do need this for the DFS. Whoops. DFS next. Maximum recursion depth exceeded. Do we have to do a BFS instead? Yeah. So the wait. I might be just not marking the things correctly then, right? Because this is very small. Wait, 0, 3, 3. Yeah, so this is just this. So groups node. Yeah, so we're gonna start with DFS 0, of course. So 0 goes to 1. And then, so groups next is not -1, so shouldn't that change groups note to group count? Oh wait, it should be if it is equal to -1, right? I think so. Cause like, so if it is equal to -1, that means it hasn't been seen before, right? But we're still not getting the right answer. Wait, why do we have that? That's very strange. Oh yeah. We need to do an else here. Okay, let's see if we are falling for any edge cases. Hopefully not. Nice. Yeah. Honestly, I don't think this question deserves to be hard. Um, like, for the AND operator, I guess it is like you need to do a DFS, and then, like, after getting all the connected components, like, you need to like see that the AND operator, like, the more you add, the smaller the number is. So you want to add all the edges. Yeah, but this question, I don't think it is hard. Yeah, but yeah. Anyways, uh, yeah, I think this question is it's very doable. But yeah, anyways, thanks for watching, and I'll see you tomorrow. Bye.